Hey everyone, coming to you from San Diego to make this video on a little family vacation, but I have a little work to get done, so let's start section 7.3. Alright, so we're going to talk about graphs, a graph of a function. So a function can be classified both by the type of equation that is used and by the type of graph it represents. In this section we will discuss a variety of functions that are described by different equations. So here we have three different formulas for equations of lines. We have standard form, ax plus by equals c. This is where x and y are on the same side of the equation. We have our more typical slope-intercept form, where the equation is solved for y. And then we have point-slope form, which we use to find the equation of the line if we're given a slope and a point. So let's talk about the slope-intercept form. That's the one that we use the most often for linear equations. So given the equation of a line, we can identify the slope and y-intercept. Slope-intercept form, get my words together, is typically y equals mx plus b, but now that we're talking about functions and we know that y and f of x are synonymous, we could also say f of x equals mx plus b. As you've seen before, m is the slope and b is the y-intercept. So we saw this in our review. The different take on it now is that we have f of x as y. And as you see our graph here, the y-intercept is 0, b, and then you have some arbitrary point on the line xy that you can count using your slope. So for the homework, we're going to see a couple of examples. And we're going to identify the slope and y-intercept of each line graph, and then the additional piece to this is identify the domain and range of each graph. So you may hear some background noise. Those are just vacation noises. Ignore those. All right, so we have number 1, 4x minus 2y equals 6. The first thing we need to do is solve for y. So I'm going to rewrite this. And then we need to subtract 4x from both sides. Now again, I write the negative 4x in front because I want to mimic y equals mx plus b. So I get negative 2y equals negative 4x plus 6. Divide everything by negative 2, and I get y equals 2x minus 3. So in this particular example, the slope is 2 over 1, and b is negative 3. So I'm going to start down at negative 3 on the y-axis, and then I'm going to count up 2 and write 1. Up 2, write 1, graph points, and then draw my line. Now for the domain, remember it's the leftmost point to the rightmost point, and in this case, this graph goes to the left forever and goes to the right forever. So in set notation, that's what my math lab asks you to use, so we'll go ahead and use that here. We get all x such that all x such that x is a real number. And then for the range, the bottommost to the topmost point, well, this graph doesn't have a bottom and it doesn't have a top, so same thing for y. All y such that y is a real number. And then we close it up. Now another way to write this, which would be totally fine for me on the midterm, is to write a fancy r. It's an r with an extra line through it. That's another way to say all real numbers. So that's totally fine too. It doesn't matter to me as long as you're telling me that there's no restriction on the domain and range. Let's switch colors here. Get a different color as they're going to run into each other in a bit. Now, for number 2, we have sort of a special case because we have a vertical line since x is equal to negative 2. And in that case, we have no y variable. And since there's no y variable, we just end up with a vertical line through negative 2 on the x-axis. So here's negative 2, and we just draw the line straight up and down. Now this one, for the domain, it's going to look a little bit different. It's not going to be all real numbers, because this particular graph only uses x equal negative 2. There's no other x values. So you literally write such that x is equal to -2. Now for the y's, your range, this graph goes up forever, it goes down forever. It doesn't go left and right forever. It just hits -2. So the range is similar to number 1, all y such that y is a real number. So vertical lines, you're just going to have a single number for your domain because that's the only x value that's ever taken on. If you look at those ordered pairs, you would have -2, 0, -2, 1, -2, 2. The x keeps repeating as -2. All right, let's move on. So now, let's kind of talk about what a function is, recall the vertical line test, and then look at a couple different lines here. There's a couple of things that you're going to want to notice as a pattern if you haven't picked up on it before. All lines are functions except this is our special case. This is not a function. And that's because it doesn't pass the vertical line test. I can draw a vertical line here and it crosses everywhere, definitely more than once on that line, but every other line is a function. So only a vertical line is not a function. There's no y value, so you couldn't write it as f of x equals anything. So that's another kind of hint. The other thing that you might want to notice is that with a horizontal line, this one's horizontal, you just have y equals. Notice the slope is 0. Here, you have an upward facing line, and notice the slope is positive. And here you have a downward facing line. And if you were to solve this, you would subtract 2x and divide by 3. You would get -2/3 for the slope, or the slope is negative for a downward facing or downward sloping line. So, and that's a general pattern that you know is true all the time. So let's talk more about linear functions. So now we know it's off limits. We can't rewrite in function notation with vertical lines, but every other line we can use f of x because they are functions. So linear function, same definition as y equals mx plus b. Now we just replace y with f of x everywhere. So nothing different than what you've seen before. Just get used to the f of x notation. So here we want to graph f of x equals 3x plus 2. Well, in this case, remember this is the same as y equals 3x plus 2. So your slope is 3 over 1, and your y-intercept, b, is 2. And you can write that as an ordered pair or not. If you write b, that's implied y-intercept, which means it's a point on the y-axis. All right, so if we graph this, we start up at 2, and then we move up 3, right 1, up 3, right 1, and then we graph that line. Notice here they don't ask you about domain and range. All you're doing is graphing. For number 2, switch colors here. For number 2, remember this is the same as y equals 3. Well, when you just have y equals, this is just going to be a horizontal line. So you need to remember that x is vertical, y is horizontal. Anytime you have x equal a number, that's the same as a horizontal line, or sorry, vertical. That's a vertical line. And in that case, the slope is undefined. There's no run, so you're dividing by 0, so it's undefined. But if you have y equals a number, that's the same as a horizontal line. They mean the same thing. And you know the slope is 0, meaning it's a solid flat line, straight left-right line. All right, so this is going to be a horizontal line through 3 on the y-axis. So right here, and then you just graph that line straight across. Okay, great job. Let's kind of move on here. So let's talk about other types of functions, mainly nonlinear functions. So nonlinear functions. We have a couple that we're going to study in this class, and then we'll get, if you move on to pre-calculus, you'll get even more in depth. Otherwise, this is a pretty good idea of sort of what's going on with nonlinear functions. So a function for which the graph is not a straight line is a nonlinear, meaning not a line. functions. Some important types of nonlinear functions are listed below. So we have 4 listed here. We have the absolute value function, a polynomial, a quadratic, and a rational function. So absolute value function has absolute value bars in the actual function. And the graph is a V-graph. I don't know about that pen color, so I'm going to switch the pen color to something that may show up a little bit better. Now a polynomial function is just has higher order exponents. So here you have an exponent of 3 rather than 1, meaning if you took out these first 2 terms and just had 5x minus 5, it would be linear. But now since you go all the way up to 3, it's actually a cubic function. So in this case, a polynomial function, or this would be, in our case, polynomial, then we just have kind of a function. If I were to write out a little tiny t-table, this one would look something like this. They're just kind of smooth and continuous curves, either both ends, one end opening up, one end opening down, or both ends opening up or down. But this is a polynomial. And they're always smooth, meaning no sharp points like the V-graph, and continuous. And you don't need to know the graphs. I'm just kind of showing you the difference here between linear and nonlinear, that you're not getting straight lines, basically. Okay, now, number 3, the quadratic, or the third one down here in this list, he's a polynomial function. He's just a special type of polynomial function called quadratic. And he's quadratic because he has a highest exponent of 2. And that makes him quadratic. Now, quad doesn't come from 4, even though you would think it would. It actually comes from square, because how many sides does a square have, or the area of a square is x squared. And so when you're thinking of quad, I want you to think area of a square, which is x squared, because it's like area is length times width, and the length and the width are the same measurement because it's a square. So when you think quadratic, just think square. And so now any quadratic actually looks like either an upward-facing parabola or a downward-facing parabola. So I'll write here parabola. Notice smooth and continuous. The rational function, he is not continuous. So rational function means there's a variable in the denominator. If there's a variable in the denominator, then you got yourself a rational function. So what does he look like? I'll kind of come over here. He has these sort of corner graphs, if you will, and it's discontinuous. You jump, you have to lift your, what discontinuous means is you have to lift your pencil to be able to continue the graph. And so we would have to lift our pencil to be able to continue that graph. So he's discontinuous graph. So note that linear and quadratic functions are just special types or kinds of polynomial functions. So what are you responsible for? Well, your homework is going to ask you to classify each of the types of functions. So number 1, f of x equals x squared plus 5. So what type of function is that? Well, the largest exponent, a good thing to look at is there's no absolute value bars. There's no variable in the denominator. So that leaves us to a polynomial. Is it a special type of polynomial function? Meaning, is it degree 1, x to the first, or x squared? In our case, x to the first would be linear, x squared would be quadratic, and we have the x squared. Oops, that didn't circle the 2 very well, did it? X squared, so this is quadratic. And so one of the things you need to know about all polynomial functions, the domain of all polynomial functions, is all real numbers. There's no discontinuities, there's no division by 0 in the denominator or anything like that. So domain is going to be all x, such that x is a real number. Or remember, you can use that fancy R if you were in a testing situation with me. All right, number 2. Let's switch colors here. Number 2. Number 2 has x to the 6 as the highest exponent. We don't have a fancy name for x to the 6th, so we just call him a Number 3, he really has x to the first, and if you have x to the first power, that's our linear function. That's what we had been graphing. So we could graph this. This would be a line. We would start at -2, b would be -2, and the slope would be 5/7. So again, domain is all real numbers. So when is the domain not all real numbers? Well, that's a really good question. This guy right here. Division by a variable, that makes this a rational function. And so in this case, you're not allowed to divide by 0, so x cannot equal 0. So that means your domain isn't all real numbers. You have to delete whatever would make the denominator 0. So this is going to be all x such that x is not equal to 0. Otherwise, the domain for us is going to be all real numbers. It's just that division by 0 that's going to change things up for us. So let me switch colors again. And let's look at our last page here. So given the graph of each function, determine the range of f. So here we have to have the graph to be able to answer this question, because range from just the function is really hard because it's all the outputs, and that's hard to see when you just have the equation. And actually we're being asked the domain too. So what is the domain? What's the leftmost point and the rightmost point? Well, this graph goes left and right forever. So the domain is going to be all x such that x is a real number. But the range, which deals with y, has a bottom. It doesn't go below this point, this line right here, y equals 0. So our range is going to be y greater than or equal to 0. Now, what kind of graph does that look like? Well, that's that B graph I was telling you about. You notice this is an absolute value function, and so that's why you're seeing that B graph. Okay, so any questions, you know what you do. And as any good math lesson finishes, let's do some word problems. So we've got a couple of cool application problems here. At least I think they're cool. So number 1, titanium trucks charge $30 for a one-day truck rental plus 75 cents per mile. Formulate a linear function to model the cost C of D of a one-day rental driven D miles and determine the number of miles driven if the total cost is $75. All right, so we got two parts. We got determine the number of miles, and then we've got to formulate a linear function. So I like to do these problems because sometimes the directions leave a little bit to be desired. So a linear function just means we need to come up something of the form f of x equals mx plus b. But instead of f of x, they want us to use c of d. Well, in order to mimic mx plus b, I need an initial value. I need a starting point. So that's what the y-intercept is. It's the initial value. It's where you're at time 0. Well, for us, at time 0, we have to pay $30 no matter what. The minute we pick up that truck, we're paying $30. So for us, b is equal to, stop erasing, b is equal to 30. Now what is m equal to? Well, m is your slope. It's your per mile charge. How are you changing as you drive? Because that's what your total is calculated by, is the number of miles you drive. So for us, we're paying 75 cents per mile. So my slope would be 0.75 dollars, right, or cents. In this case, $0.75 or 75 cents per 1 mile. So when I put that into the function, this is what it's going to look like. 0.75 times d, because in this case, where our variable of choice, which was decided for us in the problem, is d, plus how much we have to pay initially. So this is the function. When they ask formulate a linear function, this is it. If I drive 0 miles, you let d be 0, and I pay $30. If I drive 1 mile, let d be 1, I pay 30 plus 75 cents, or $30.75. So that's sort of part A. Now part B says determine the number of miles driven if the total cost is $75. So what they're telling us here is that you know C of D, the cost of some number of miles driven is $75. What you don't know is what D is. These are two different variables, even though they share D in common. C of D is a variable and D is a variable. C of D is after you plug in D, your cost for D miles. So we need to solve for D. So what do? We plug 75 in on the left-hand side. We say 75 equals 0.75D plus 30. We subtract 30 from both sides. Come over here in one more room, and I get 45 equals 0.75D. Divide by 0.75, and I end up with, and we end up with 60 is equal to D. So that means if I spent $75, then I must have driven 60 miles in order to spend that total. All right. Any questions? And then we'll move on. Okay. So, last one. Now, this particular problem we haven't seen yet, this formula that we have to use. So this one calls for a little bit more work because they don't give us the initial value. So I'm going to kind of give you that hint as we go in to read it for the first time. So number 2, in 1994, the life expectancy of males was 72.4 years. In 2004, it was 75.2 years. So notice they give you 2 data points. And in that case, we have to do a little bit more work. So at the end of the day, they want a function, E of t, to represent life expectancy and t be the number of years since 1990. Find a linear function. So again, they want this, but they want us to call it E of t instead of f of x. So what we don't know is the slope, and we don't know the y-intercept because they didn't give us any initial starting value. They didn't say in 1990 the life expectancy was. They gave us 94, they gave us 2004, but not 1990. So when they give you 2 data points, you're going to write them as an ordered pair. Ordered pairs. So what do I mean by that? Well, in 1994, you have 72.4. So now watch what I do. I'm going to write 4, 72.4, and 14, 75.2. And you're thinking, whoa, where did she get 4 and 14? Good question. The way they worded the problem, everything is since 1990. So for us, I don't write 1994 in that x-coordinate. I write 4 years because 1994 is 4 years since 1990. So it's in terms of 1990. So the first order pair is 4 years after 1990. The life expectancy was 72.4. For the next one, 2004, how many years after 1990 was that? 14 years. So you get the ordered pair 14, 75.2. Now you're wondering why write them in ordered pair format. Well, I need the slope and I need the y-intercept. Well, if I have 2 points, then I can use the slope formula to find the slope. So slope formula, remember, is m equals y2 minus y1 over x2 minus x1. And if you didn't remember that, that's okay, but this is the slope formula. Change in y over change in x, rise over run. So for us, I go in and I say, all right, we'll call him x1, y1, call him x2, y2, and I just plug into the formula. 75.2 minus 72.4 divided by 14 minus 4. And I end up with a numerator of 2.8 and a denominator of 10, reducing to a decimal of 0.28. So that's my slope. I know my slope is 0.28, and notice It's t is the variable here because it's e of t. So now I just need to know the y-intercept. Well, I know you want to know the y-intercept. So how do I find the y-intercept? Well, now I have a slope and a point. So I'm going to use the point slope formula. So we use the formula y minus y1 equals m times x minus x1. This is the point slope formula. Now for us, we have a point, I should say, put a comma between them, point. We have 2 points up here, and we have the slope right here. So we just fill in. You can pick either point, it doesn't matter, you'll get the same answer either way, it's arbitrary. So I'll pick the first point, so I get y minus 72.4 equals 0.28 times x minus 4. That look nicer. I'm going to distribute here. Come over here where I have a little bit more room. And I get y minus 72.4 is equal to 0.28x minus 1 point, looked away for a minute, 1.12. And then to get into slope-intercept form, I'm going to add the 72.4 to both sides. And so I end up with y equals 0.28x plus 71.28. Well, now that would be right if I were using y and x, but we are up here with the e of t function, so I have the 0.28x. I'm going to write that as 0.28t as I do here, and now I have the y-intercept. So this is our final answer. Yay! And so that's your function. That's the one that's going to tell us what the life expectancy will be any year t after 1990, t years after 1990. Okay, so let's answer one more question pertaining to this. Use the function in part A to predict the life expectancy of males in 2012. Well, obviously I wrote this before 2012 because we aren't predicting as much as we're looking backwards, I guess you could say. So let's switch colors here. So how would I find the life expectancy of males? Well, remember, this is our function, and there's 2 variables in this function. You have e of t and t itself. Getting towards the end here. So we have this variable here and then t itself. What did they give us? Did they give us time or did they give us the expectancy? And so for us, they gave us t. They said 2012. Well, how many years after 1990 is 2012? And you could even do the math, just finding the difference. And so you end up saying let t equal 22. And so you just find e of 22. I'm just going to close the parenthesis up. 22. So 0.28 times 22 plus 71.28. Throw that into your handy-dandy calculator. You get 6.16 plus 71.28 or 77.44 years was the life expectancy in 2012. All right, well, that takes care of section 7.3. I was almost going to say 7.4, got ahead of myself. So 7.3, the lesson was brought to you from San Diego, quite exotic, if I don't say so myself. To be continued with section 7.4.